press the button. Okay. Hello, everyone. Nice to see you again. Today we have the 7th talk in the colloquium series for this year. And first of all, I would like to acknowledge traditional owners of the Australian land and pay my respects to the elders, past and present. Today, I'm happy to present Rafael Fernandes, who is professor in the School of Physics and Astronomy in the University of Minnesota. Rafael is one of the leaders in strongly correlated materials and unconventional superconductivity. Rafael received his PhD degree from the University of Campinas in 2008, and after 2 postdoctoral appointments in Ames Laboratory in Iowa State University and a joint postdoctoral appointment in the Columbia University and Los Alamos National Lab, he joined University of Minnesota in 2012. He has got a number of prizes, including fellowships from the American Physical Society, George Taylor Distinguished Research Award, and Department of Energy Newly Carrier Award, and a few more. Okay, so Rafael, the stage is yours, and we will enjoy the talk.
Thank you very much, Dimitri, for the kind introduction. Thanks for the invitation to speak here. So today I want to tell you a little bit about our current or what we've been working on, which is this idea or this concept of intertwined electronic phases. And please interrupt me at any time with questions. So this work, I enjoyed collaboration with many people. I'm highlighting here some people that were in my group and now are in different positions all over the world, and people currently in my group, and then many external and UMN collaborators, including the experimental groups that I put here. And of course, the funding that has been essential to do all this research. So this outline of my talk, I'll start about introducing what quantum materials are, or at least what I consider to be quantum materials. Then I'm going to give an example of intertwined orders, which is the Pneumatic Phase. And then I'm going to finally go in original work that we did about 2 different kinds of vestigial orders. One, vestigial magnetic orders and the application iron-based superconductors, and also vestigial superconducting orders, which has some application in twisted bilayer graphene. So I thought I would start from the very beginning about what is the standard model of condensed matter physics, which we all learn. We have essentially a gas of nearly independent electrons hopping on a lattice. And we know how to solve this problem very well. We just use Pauli principle and we fill up all the energy levels until the last one. And that's when we get the Fermi level and a well-defined surface in momentum space that divides the occupied states from the empty states. And what we also learn is that the moment, if you turn the Coulomb repulsion on, if you do that in a adiabatic or in a slow way, the main point of Landau's Fermi liquid theory is that this electron gas becomes an electron liquid where the electrons are dressed by these interactions. They are not anymore long-lived, or they're not anymore electrons, but they are excitations that we can call quasi-electrons, in the sense that they have the same quantum numbers as the electrons, the same charge, the same spin, the same orbital, but now they have a different mass, and they also have can have a finite lifetime. So here's an analogy of what is between an electron and a quasi-electron. So this is, you probably saw this news, I think it's from a while ago. This was a fresco by Elias Garcia Martinez. And this was news because this was a fresco in Spain that needed some restoration, and some local person decided to do the fresco on their own. So the idea here to show these pictures is to show that the original fresco and the restored fresco are like the electron, the quasi-electron. You can see that they share the same quantum numbers, the same properties, but there's still some differences between them. And the implication of this idea is that we essentially can describe the collective behavior of these many electrons as just essentially the same behavior as an individual electron. Okay? And this description has been very successful in leading technologies and understanding of metals, insulators, semiconductors. But what we're interested here is in what goes beyond that. We're interested in the so-called quantum materials, right? And this word has been used a lot and probably means different things for different people. I'm just showing here that the University of Oxford has a quantum materials coloring book, and even defines here what is a quantum material. I'm going to use, so according to this definition, is something with interesting properties that can only be explained using the theory of quantum mechanics. I'm going to use a little bit more restrictive definition, which is I'm going to refer to a quantum material when the collective behavior of the electrons is different than that of an individual electron, right? So this goes back to ideas that date from this paper by Phil Anderson about emergency, or the idea that when you put a bunch of particles that are interacting together, the emergent behavior can be very different than the individual constituents. So in particular, the systems that I'm interested in, this collective behavior that is unique arises either because of Coulomb repulsion that is too strong to be treated in the way that I described before. These are the so-called strongly correlated systems, or because of the topology of the wave functions. These are the topological systems. So if you want an analogy, is the same. An analogy would be the difference between birds, individual birds, versus a flock of birds that act collectively different than how a single bird would do, right? So as I mentioned, when we describe an electron, we describe in terms of its quantum numbers, the charge, spin, and orbital. They are the same in the Fermi liquid or in the Fermi gas. Now, in these quantum materials, several different things can happen. One remarkable thing that can happen is that these quantum numbers fractionalize. In other words, you get a quasi-particle, an excitation that has a charge but no spin. That's called a holon, or a spin without a charge, a spinon. Okay? Another interesting possibility is because of the magnetic ground state, and this here's so-called spin ice, the excitations behave as something that has nothing to do with an electron. So the excitations here behave as magnetic monopoles. Or sometimes the electrons they bind together to form a Cooper pair, which is a boson, and then has different properties. So all of these I'm going to put in the category of quantum materials. And one other remarkable property is that in a lot of these quantum materials, these quasi-electrons, these quasi-particles, they become so short-lived that you cannot even think of them as a quasi-particle anymore. They become incoherent. So in that analogy to the fresco that I show, so I use here, I forget what's the name of this program that makes any picture look like a Picasso picture. So you can see already that this becomes what I would call the incoherent fresco in this analogy. And this is believed, or this is known to give rise to what is called strange metal behavior. So why should we care about this? Well, perhaps the next generation of technologies will be based on the fascinating properties of these quantum materials, right? So I think probably the example that everybody talks about is the high temperature superconductors. Colossal magnetoresistance systems. We have also spin liquids that arise here. For example, this is an organic compound. We have the quantum version of liquid crystals, the so-called electronic liquid crystals, and topological systems. So just to give you an example, everybody talks about how high temperature superconductor can affect new technologies. One interesting way, which is to produce very strong, stable, high magnetic fields that, for example, can be used to design a new fusion energy facility, for example, or not even a facility. This would just be a very low cost, portable energy device that creates fusion energy. And then again, would be an application they've been testing using high temperature superconductors, these companies here to do that. Okay? Just as an example. Right, so how do we go around to solve this problem? Well, we have a problem of 10 to the 23 interacting electrons that are, we know the Hamiltonian, we know very well what it is. We have the electrons, the ions, and the Coulomb interaction between them, but it's very complicated. And so one idea that I'm going to do here is exploit this concept of emergency, right? And there are lots of different ways of approaching the problem. You can develop low energy models that you can calculate, do analytical calculations, for example. You can simulate low energy models. But what I'm really going to talk about here is how we can do phenomenology beyond just mean field that can help us understand this and connect to experiments. So to talk about phenomenology, let's go to a very simple case that was well understood, which is the phase diagram of water, the gas, liquid, and solid phases. We can describe this very well without actually knowing the microscopic details by just writing down a Landau free energy. And you can extend this to quantum systems. Here's helium-4, which has very similar phases, a liquid phase, a superfluid phase, which is now the a quantum phase, a solid phase, a gas phase. And you can ask whether you can do the same phenomenology to the quantum materials. And one thing that you see, I'm just putting here 3 different phase diagrams. One immediate thing that you see in them is that you have a lot of phases that show up here. I'm not going to go into all these details, but they share similar transition temperatures, similar energy scales. It's not just different phases, but they seem to have some connection. So, for example, in the cuprates, you have charge order, spin order, superconductivity, pseudo gap, all similar energy scales. In the iron-based superconductors, you have pneumatic and magnetic and superconducting. And here's an example of manganites with more phases. So the idea that has emerged, and I think it was also articulated very nicely in this review paper by Fradkin, Kivas, and Tranquada, is that these are not, shouldn't think of these as competing or phases, but as intertwined phases that have a deeper relationship than just independent degrees of freedom. And this is the topic of this talk. I'm going to focus on one realization of intertwined orders, which is the concept of vestigial phases. And that's what I hope to accomplish during this talk. I will show you examples where we don't need to have fine-tuned parameters to get different phases that have comparable energy scales and break symmetries that are different. Okay? And this is actually has a lot of applications to actual materials, to the phase diagrams of quantum materials. And I'll try to explain and give some examples next on how this happens. Okay, so let me go to an example, which is the spin pneumatic case. So let me start with possibly the simplest electronic order state that we find in nature, which is the ferromagnetic phase. I'm just showing the spins of the electrons, and in the ferromagnetic phase, they all align in one direction. And we understand microscopically this comes from Coulomb repulsion and Pauli principle. If I represent this in spin space, all it means is that in the sphere, the spins chose one direction to point. Okay, and we can describe this. We know that as we go up in temperature, the system has a phase transition to a paramagnetic phase, because in the paramagnetic phase, there are more states available, the entropy is larger, so at some critical temperature, you go to the paramagnetic phase. We can describe this without knowing any microscopic, by just using the prescription of Landau theory of phase transitions. We introduce an order parameter, which in this case is the magnetization, just average of all the spins. And we know that in the ordered state, the spins are aligned. This is non-zero, the average value, whereas in the disordered phase, it's 0. So what we can do, since we know that the free energy of a system is an analytical function, we can expand using symmetry arguments the free energy in terms of this order parameter. So the symmetries only allow terms that are the scalar product, and you can have, and it has to be analytic. So we have eta squared or eta to the power 4th. And as we know very well, you can minimize this free energy. Above Tc, the minimum is at 0. Below Tc, this coefficient changes sign, and you get a finite value here. We understand this very well. Now let's look a little bit closer to what symmetries are being broken here, right? So in spin space, I mean, there's no symmetry being broken here. I'm considering in real space. So let's just focus on spin space. So above Tc, the spins can point in any direction. So the system, we have spin rotational symmetry. Below Tc, spin rotational symmetry is broken. So this is a continuous symmetry that is broken. Time reversal symmetry is also broken because under time reversal, spins up go to spin down. And because the spins chose a direction, it also breaks. That's great. But then here comes the question. Can these two symmetries, do they need to be broken at the same temperature? Or can they be broken separately? So if you look at it, time reversal symmetry means that I choose a direction in spin space. That necessarily implies that I break spin rotational symmetry. The converse is not true. I can break spin rotational symmetry without breaking time reversal. For instance, let's say that I force my spin to point only to be constrained in this cylinder here, so it can point up or down, but it still doesn't break time reversal symmetry. So the question is, can I break this spin rotational symmetry before breaking time reversal symmetry? To answer this question, let's go back to the classical example. It's always good to make the connection. So you can ask something similar about the solid liquid phase of phase transition of water, right? Because there are also two symmetries being broken. Here is a depiction of the molecules, of the water molecules, and in the solid phase, they form a lattice, which means they break both translational and rotational symmetry. In the liquid phase, both symmetries are restored. The system has translational symmetry and rotational symmetry. So can they be broken separately? And the answer is no. In the phase diagram of water, or in water, there's no way you break one without the other. There's a phase transition. We know this very well. But there's another class of classical systems where these symmetries are broken separately, which is the liquid crystals. So liquid crystals, you can think of them as rod-shaped molecules, okay? And here's a crystal phase of a liquid crystal. So you see that these molecules are all aligned, and their center of mass forms a lattice. That's a crystal phase, doesn't have translation, or it has a translational symmetry, but not in continuous translational symmetry. And same for rotational symmetry. And this is the liquid phase where these molecules can point in any direction. The center of mass is in any position, so they have full translational and rotational symmetry. And you can go from one to the other by melting. But there is an intermediate phase, and that's why these are called liquid crystals. It's a phase that is intermediate between a liquid and a solid, and that's called a pneumatic phase. Okay? So in the pneumatic phase, these broad molecules, they point more or less in the same direction. So we break rotational symmetry, but their centers of mass is still randomly positioned, so you preserve translational symmetry. So this phase, the pneumatic phase, is intermediate, and that's how you can break two symmetries in two steps. You can think, there are several ways you can think of them, but you can think of the pneumatic phase as a partially melted crystal, or as a vestige of the crystalline phase, in the sense that a vestige is according to Google, is a remnant, a trace of something that exists, that no longer exists. So this phase here knows that there was a crystal before because it keeps the rotational symmetry breaking, but restores translational symmetry. Now we can go back to the idea of the ferromagnet and ask whether this can happen there. That would be what people have called, and again, this is work going back to more than 50 years ago, a spin pneumatic phase. That would be a phase where you break spin rotational symmetry spontaneously while also preserving time reversal symmetry. Okay? And the question is whether there is a model or there's a way of describing this spin pneumatic phase from the same degrees of freedom that I have to describe ferromagnetism. So the first question is, what's the order parameter? So the key point is that you don't need to add a new order parameter. You can use the order parameter that we had before to build this new one, okay? So how will I describe this phase here that has time reversal symmetry, but no spin rotational symmetry? Clearly, if time reversal is preserved, the expectation value of eta has to be 0, otherwise it'll break time reversal. So it has to be quadratic in eta. It can't be the scalar product because that's, of course, invariant under any rotation. Doesn't break any symmetries. What I need is really an errorless vector. And that's, again, where we can borrow this concept from liquid crystals. We can build an errorless vector by defining this tensor order parameter. So this is a traceless symmetric tensor, which defines a direction without an arrow. Or if you wish, this is the same as a quadrupole moment of the spin density, if you wish. Okay. So, but this is the key point. I have, with a single set of order parameters, I can describe, or just one order parameter can define both phases. I can define the spin nematic is this tensorial, is a composite order parameter, right? And I can define the ferromagnetic order parameter, which is the primary order parameter. And in this regard, the spin nematic phase is a vestige of the ferromagnetic phase. And we can say that these two phases are intertwined because one order parameter is the composite of the primary one, okay? And already, again, 50 years ago, in this paper here, the authors proposed a model that realizes the sequence of phases. Of course, the question is there material that realizes this phenomenon? This is a very active area of research. One of the problems, of course, is that once we have a crystal, spin rotational symmetry is explicitly broken because of the lattice. But there are spin-1 quantum magnets where, because of the quantum nature of the spins, you can actually have a property that is equivalent to a spin nematic phase, and there are signatures that are consistent in these two materials of a spin nematic phase. So this was to give an example, and now I can extend this to a much broader context, which is the idea that of a vestigial phase, right? The idea is I have a primary order parameter, which has to be here a multi-component order parameter, which I call here eta alpha. Alpha is just the components. So that when the primary order sets in means that this primary order parameter is non-zero. The disorder phase, disorder parameter is 0. But again, I can now build tensor order parameters or composite order parameters that are non-zero in the primary phase, non-zero in the vestigial phase, but 0 in the disordered phase. Okay? So again, this only happens if this combination here breaks a symmetry, which is what I explained before. So this idea of a vestigial phase naturally leads to intertwinement between the primary order and the vestigial order because they're deeply connected. And by the way, this term vestigial order, as far as I know, was first coined in this paper here by Steve and Lai Mei. And it's a very nice extension of this concept of electronic liquid crystals. Okay. Now, of course, that this idea has been around. People that work on frustrated magnets will recognize that another example of this is the order out of disorder mechanism. I'm just putting this in a more formal ground to apply to other systems.
Rafael, could I interrupt you?
Sure, yeah, please do.
So many phases that are preceded by fluctuations. For example, in superconducting state is preceded by superconducting Cooper pair fluctuations, where the order parameter is 0, but the average value of its squared amplitude is non-zero. Is it related, or how to distinguish it from the picture of just fluctuations?
So it is different. I think the example would be the equivalent of here, right? Because what you're describing are amplitude fluctuations or phase fluctuations. They do not break any symmetry, right? They are present at any temperature. Of course, they build up as they get closer to TC, but they are not a symmetry breaking fluctuation channel. On the other hand, this particular combination that I had here it does break a symmetry, right? So you can think of these as fluctuations that break symmetry. It's an abuse of language, but it is beyond just, I mean, they're connected, right? You're going to need these isotropic fluctuations to get this order parameter to condense, because these are also fluctuations. But you can separate the fluctuations in different channels if you wish.
Okay, I see. Thank you.
I'll give an example actually of a vestigial superconducting phase that hopefully will help clarify this a little bit more. Right. So we can, now that we have this idea, we can, now a key point, as Dimitri just referred, mentioned here, is that I need fluctuations. If you do mean field, this never happens. So you need to go beyond mean field, but it's still phenomenology. And you can get a rich variety of phase diagrams. And the key point is that these two phases, whatever you do, you get them to have similar transition temperatures. They have similar energy scales. And there's a lot of different possibilities for these phases. Different phases can have the same vestigial phase, for example. There can be a vestige of a vestige. There are lots of different possibilities. And then the rest of my talk, I'm going to talk about two of them. So the first one is vestigial magnetic orders. And again, all these vestigial phases I want to apply to a material where, this concept can help us understand something. So let's see about the iron-based superconductors. So they were discovered about 14 years ago. They were the second family of high-temperature superconductors. They have this basic structure, which is a 1 iron per unit cell. Or sorry, 1 iron atom. So the iron atoms forming a square lattice. And then on the center of the plaquettes, you have 1 arsenic above and 1 below the plane. So this is this puckering here. And so this is so there are 2 iron per unit cell. And this is one of the many phase diagrams that can appear. Often, but not necessarily, you have an antiferromagnetic ordered state at zero doping or zero pressure. And then here, for example, you're replacing iron by cobalt, so you're adding an extra electron. You suppress this magnetic transition, and then you get a superconducting dome. Okay, this is not very high, but there are other higher transition temperatures. So if you look a bit at this magnetic phase, you see that it's not ferromagnetism, it's actually a stripe antiferromagnetic phase, which means that the iron spins are parallel along one direction and anti-parallel along the other one. If I define an order parameter that is just the magnetization as I defined for the ferromagnet, I get 0. But of course, if I define the stagger magnetization, where for every, so when I change my column, I multiply by -1, then I get a finite stagger magnetization. That's my order parameter. Now, this ordered phase here breaks 2 symmetries. Again, one is spin rotational or translational symmetry. And the other one is the tetragonal symmetry. This no longer has the symmetries of a square. As you can see, these two atoms here, their spins are parallel, but these two here are anti-parallel. So this breaks the equivalence between X and Y. And the question again is, can they be broken separately, these 2 symmetries? So to construct a theory, we need to realize that there are actually 2 different magnetic ground states that are degenerate. One is this when the spins are parallel along Y and anti-parallel along X, that's what I call eta1. And the other is when the spins are parallel along X and anti-parallel along Y, that's what I call eta2. They are related by, you see that I cannot just do a spin rotation to go from one to another. I need to do a spin rotation and a real space 90-degree rotation. Okay? And you can see that what it means is that I can write down this order parameter eta1 square minus eta2 square. When it's non-zero, it means that fluctuations are different along the X and Y directions, and they break rotational symmetry, the 9-degree rotational symmetry. And I can do that even though there's no long-range magnetic order. So another way to think about this is that these spins are not ordered, but they are fluctuating in a way that these 2 are locked to fluctuate in an anti-parallel fashion, and these 2 are locked to fluctuate parallel to each other. So it's still fluctuations, but they break a symmetry. And Dimitri's question would be, if I put a plus sign here, then there's no symmetry breaking. This is just what I would call standard magnetic fluctuations, right? And this here is a discrete symmetry breaking because I choose between X and Y. It's an IZ symmetry breaking. I'm not going to give you any technical details, but you can write down your theory of free energy in terms of the zetas, and you can do beyond mean field calculations. This is the result of a large N calculation, which includes fluctuations in a self-consistent way, which actually also agree with normalization group calculations. You get this split transition where you break the tetragonal symmetry, and another one where you go to the magnetic phase. They are following each other, and then they actually merge in a single first order transition. Okay. Now, this is what we call the pneumatic phase because it breaks rotational symmetry. It's different than the spin pneumatic I mentioned before because this is a breaking of rotational symmetry in real space. Okay. And if you look at this phase diagram, there was another phase that I didn't mention to you, which is this red boundary here, phase boundary, that separates the tetragonal to orthorhombic. That's precisely this pneumatic phase. The tetragonal to orthorhombic is a 9-degree rotational symmetry breaking. And you see in the phase diagram how it's always very close to the magnetic phase. In this formalism, this comes naturally as this is the pneumatic is a vestige of the antiferromagnetic phase. You can ask, how can I actually prove that, or can I demonstrate it is actually the case? So using the same form, yeah.
Raf, could I interrupt you again?
Oh yeah, please.
Could you return to the previous slide?
Yeah.
You have a dashed lines on a phase diagram. And
this one, the theory or the experimental one?
On the left one.
Yes.
And the normal one. I mean, is there any reason so the transitions are different? From the point of view of the phenomenology.
Yeah, right. So here they are two separate second order transitions. And here they are simultaneous first order transition. Notice that there's no scenario in where you have a single second order transition. Either you have two separate transitions that can be both second order, one second and one first, or both first, or a single first order transition. But the other is not possible. This dashed has a different meaning. In this phase diagram here, this dashed is just a guide to the eye. I mean, it's not really, you have just one data point, two data points here that you connect, but whether they merge or not, this is also inside the superconducting state, which is a little bit different. Did I answer your question?
Yes, thank you.
Now, I just mentioned that with this formalism, you can go beyond and you can actually derive a general relationship between the elastic fluctuations and the magnetic fluctuations. The elastic fluctuations come from the pneumatic, which come from the magnetic. So you can derive this scaling between the shear modulus and T1T, which is the NMR spin lattice relaxation rate. And then again, you derive this relation. Now you can see, you can measure both of them separately, the shear modulus and T1T, and you can see if they satisfy this relationship, and they do satisfy pretty nicely this relationship as shown here in this paper here. So this was for one compound, and later the group of Wanna Bommer and Christoph Meingeist extended that to other compounds as well. So this shows that the elastic fluctuations are intertwined with the magnetic ones. Now, you can take a step back and say, okay, if I write down a model for these two order parameters, eta 1 and eta 2, is the striped spin density wave the only game in town? And the answer is no. You find out that there are two possible other phases that can appear. One is what's called a charged spin density wave, where one of those eta 1s is, both eta 1 and eta 2 are non-zero and parallel, or what we call the spin vortex crystal, where both eta 1 and eta 2 are non-zero, but they're perpendicular. Okay? So that this was possible within the same set of models was already recognized very early on in the field of pnictides by Pepe Lorenzana. And these are just different configurations that you can build from the same set of order parameters. You can ask, how do I decide between these three phases? And what you found out when you did the randomization group calculation is that when you combine spin-orbit coupling, in proximity to a quantum phase transition, you find that the degeneracy between, that it will get an extended, an enhanced symmetry, a closer degeneracy between these different phases. So the expectation is that as you approach this quantum phase transition, these other phases that I didn't mention to you, this charged spin-dense wave or spin vortex crystal, should start appearing. And that is actually what they see in some compounds, in some hole doped compounds, as they start approaching hole doping, optimal doping, they see the appearance of these other phases here, as I'm showing here, okay? And this is another instance of intertwined orders. You have 3 different magnetic ground states that, however, come from the very same mechanism. Now, that actually brings the question, if these 2 other phases are realized, do they also have a vestigial phase, right? Remember that the striped spin-dense wave break the equivalence between X and Y, the 9-degree rotation. What about these other 2? Do they have any sort of vestigial phase? You can see immediately that they don't break tetragonal symmetry. They don't break the equivalence of X and Y. So if there's a vestigial phase, it'll be something else. And actually, in both cases, they do, as long as fluctuations are present. The charged spin-dense wave has a vestigial charge density wave, where these sites here that have, this is a non-uniform phase, by the way, where you have Niel order in one sublattice and no order in the other. And in the charge order of vestigial phase, you have larger charge in one of the sublattices than the other. But what I want to talk to you a little bit about is the vestigial of this very unusual phase, which is spin vortex crystal, okay? It's a non-uniform, non-collinear phase where the spins form these vortices around the plaquettes, okay? And the vestigial phase is actually a spin current order. Let me explain a little bit more. So, as I was mentioning to you, we can construct this order parameter, which is the cross product of the 2 primary orders, and you can take scalar product with Z. And this, if this is non-zero, it corresponds to a spin current. What does it mean? Think that in a plaquette, I have a current that is spin polarized, and it alternates between clockwise and counterclockwise. Okay? So this is the prediction. It has the same symmetry as an electric field, if you wish. Okay, so this prediction was that these spin currents could be a vestigial phase of this spin current. And then we can understand how would they be manifested, right? So think about spin currents. So I just drew here spin currents that have, let's say they all spin up. I have a spin current and that is staggered. So in different plaquettes, they have opposite orientations. The same way that a charge current generates magnetic field, a spin current generates an electric field. And the electric field here is such that it points up here and down here, and then it alternates. But remember that I told you the arsenic atoms, they are staggered, right? They are pointing up and down, or above and below the iron plane. So it means that all the arsenic atoms will experience the same direction of the electric field. So if you just imagine that this arsenic has some charge, it will move not symmetrically with respect to the iron plane. So the key point is that these 2 arsenic atoms become inequivalent in this vestigial spin current phase, okay? This has very interesting effects. One of the effects that we find out is that if the spin current is present, if you apply an in-plane magnetic field, again, I go back to there's no magnetic order. If I apply an out-of-plane field, I have an out-of-plane magnetization. That's just a standard paramagnetic behavior. But here is actually pretty bizarre. If I apply a field in plane and I have these spin currents, I not only get a component of the spins pointing parallel to H, but I get a component that is perpendicular and staggered. So a magnetic field here induces both ferro and antiferro orders, if you wish. And you get a scanted phase here. So this would be a direct evidence that the spin current phase exists. Another even more interesting effect is on the band structure, because you break the inversion with respect to the iron plane, you actually lift the symmetries of the system. So when you apply a magnetic field, you can actually induce Weil points, which I'm not going to discuss in much more detail, but that would be a way of the vestigial order inducing a vestigial order inducing topological phenomenon. And then, of course, a question is, okay, so, but does this happen in any iron-based superconductor? Well, there's one where the spin current is almost built in. This is the so-called 1144 family. So this is, here's an example, calcium, potassium, iron 4, arsenic 4. So you see that this is a bilayer system, and the layers are separated by a potassium atom here in the middle and calcium here above. So it means that this arsenic here sees calcium, and this is, sorry, this is potassium, and this one sees calcium. So these two arsenics are different. So this is an explicit symmetry breaking by the crystal field. Now this compound has a magnetic order, and because I have this, because there's this small symmetry breaking field, it favors the phase that is compatible with this vestigial order, which is the spin vortex crystal. And this was observed experimentally. And MR showed that this is exactly the phase realized when you dope this compound. So this actually would offer a nice way to look for these Weyl points as well. Okay. So now for the last part of my talk, I want to talk about a different kind of vestigial phase that happens in superconductors. So when you go to talk about superconductivity, the order parameter now, as we know, is a complex number, a wave function that has amplitude and a phase. And the symmetry is this U1 gauge symmetry, right? And as we know, a finite eta opens a gap in electronic dispersion. And generically, if you have lattice vibrations, they can mediate pairing. We get a conventional superconductor. So here's a plot of a conventional gap. Around the Fermi surface is just uniform, essentially, isotropic. But as we know, if we have electron-electron interactions, even though they're repulsive, they can mediate pair interaction that is in the unconventional channel, and usually you get a gap that is anisotropic or sign change. Now, the key point is that there are superconductors, there's a class of superconductors that break additional symmetries of the system. I'm talking about two of them here. One is a chiral superconductor that also breaks time reversal, and the other is a pneumatic superconductor that breaks lattice rotational symmetry. And all of them require that my order parameter has two components. So I have two gaps, actually. Or in the language of group theory, what I'm trying to say is that the superconducting gap has to transform as a two-dimensional or higher dimensional reducible representation. And then depending on how the relative phase or the relative magnitude, you can get chiral or pneumatic, okay? So these are clear candidates for vestigial orders because they break U1 gauge symmetry, but also another symmetry of the lattice or of the system, either time reversal or a lattice rotational symmetry. So let me focus on the pneumatic superconductors. There are several candidates for pneumatic superconductors. Few layer niobium diselenide, doped bismuth selenide. There's lots of work about the pneumatic character of the superconducting phase. Whole doped iron-based superconductor. This calcium tin-3. But one that I'm going to talk about is the twisted bilayer graphene, which I'll show you has strong evidence that this is a pneumatic superconductor. So just a very quick overview. What is the twisted bilayer graphene, right? So graphene we understand very well. The band structure has these Dirac cones. The electrons behave as Dirac particles, and we all understand this very well. If you take now two graphene layers and twist one with respect to the other, by a small angle, you create a superlattice that is called a Moret pattern or a Moret superlattice. And if this angle is small, the separation between the period of this Moret superlattice is huge. For example, here's 14 nanometers, is 100 times the carbon-carbon distance in graphene. And what was proposed years ago in these papers, and this very famous paper by Bistritzer and McDonald, was that if you choose this angle just right, you get a nearly flat band. So the physics is simple. When I rotate these two, when I bring together these two graphene layers, I'm hybridizing two Dirac cones, and the hybridization opens a gap. If this gap here is comparable to the distance between the Dirac cones, I can essentially lead to a vanishing of the velocity, which would lead to a flat band. Okay. So there was the so-called magic angle where this happens, which is about 1 degree. And if I have a nearly flat band, Coulomb repulsion becomes important. And I have strong correlation effects, which don't happen in just regular monolayer graphene. So the group of Pablo Jarrillo in this, again, very influential paper in 2018 showed that indeed, if you twist bilayer graphene with this magic angle, you see a correlated phase, insulating phase near half filling, followed by 2 superconducting domes. So this is the first observation of a superconducting phase in a graphene-like system, again, that is not induced by a dopant. And then after this, several other groups by Andrea Young, Cardin, and Afetov, and Stephen Nagy-Purge, they all found very similar behavior. And now we understand very well this is a phase diagram showing the superconducting domes, the different TCs that you can get depending on the angle and different compounds, and the appearance of these insulating phases near half filling. Okay, let's now talk about this superconducting phase here near the whole dope side of the phase diagram. So the group of Pablo Jarrillo, what they did was to look at the magnetoresistance or the HC2 or HC, sorry, the in-plane critical field, the angular dependence of the in-plane field. And what they saw, surprisingly, was a twofold signal, very strong twofold signal, which is very odd given the fact that, as you can see, this lattice has 6-fold, not twofold symmetry. So one, I can explain more the fact that this twofold anisotropy axis rotates is a very strong indication that this is a spontaneous pneumatic superconducting phase, meaning that the pneumatic phase, the pneumatic gap function, as I'm schematically plotting here, breaks the threefold rotational symmetry into 2. Okay? And there have been different models, different ideas to try to explain that. Now, again, now I can apply again this idea of the vestigial phases. I have a superconducting phase that breaks gauge symmetry, but also breaks threefold rotational. And the question is, can they be broken separately? You can do a calculation. The main difference now is that the composite order parameter is a 3-state pot, no longer Ising, and it can break at different temperatures. And is there evidence for that? Well, if you look at this resistivity and isotropy plot, RxY here is really a measure of the resistivity and isotropy of pneumatic order. There's a huge contribution from the normal state, but near the superconducting dome, there does seem to be some potential for a vestigial pneumatic phase. And the same idea of a vestigial pneumatic superconducting phase was also proposed by Matthias Hecker and Jörg Schmale in the context of bismuth selenide. But then when we look a little bit more carefully here, we see that there's another possible vestigial order that is different. So this, again, this phi is a 2-component real order parameter, is the pneumatic. I can create eta1 squared plus eta2 squared, but unlike what the order parameter that Dimitri was referring to early on, there's no absolute value. This is just eta1 squared plus eta2 squared. So this is a complex order parameter. What this describes is actually a charge for E object, a charge for a superconductor because it breaks U1 symmetry. And the square here is essentially showing you that it has a charge 4E instead of 2E. Okay? So if you wish, this composite here is a pair of pairs and is a new order parameter. And is a composite that, in principle, as you can see, as long as I have 2 condensates, I can have it. But the question is there any chance that this can condense instead of the pneumatic? And what we found in this paper with Liang Fu is that actually there's a hidden symmetry that connects these two. This is, again, a 2-component real order parameter. This is a 1-component complex order parameter. And there's a symmetry that says that they are nearly degenerate. So if there is a way of you suppressing the vestigial pneumatic phase, the expectation is that the charge for E phase will show up. So and again, this all is rooted in this hidden discrete symmetry that's called a perfect shuffle permutation symmetry. And we know that the nematic is very sensitive to random strain because it couples linearly with strain. We know that the three-state Potts model in the presence of random strain has no order in two dimensions. So if you have an inhomogeneous system with random strain, it is possible that you're going to stabilize a charge Fourier phase instead of the nematic phase is the vestigial phase. Now, just, there's an idea.
Could I interrupt you again?
Yeah, sure.
If you return from the phenomenology to the microscopic picture, does it mean that charge for order parameter corresponds to the average value of 4 fermionic operators?
Yes, it's a quartet. Yes. Yes, and actually I was going to mention here that this has a long history. That people have thought about quartets in lots of different contexts. This is a paper by Nozier and St. James where they discuss if you have a Bose-Einstein condensation, can you have a pair of bosons condensing before the Bose-Einstein condensation, which is equivalent of a quartet here. So all these papers here have discussed different scenarios where you can have this quartet forming. There's this very nice paper by Aris Berg, Edward Fradkin, Steve Kivelson, where they show that if you had pair density waves, they could melt in a charge Fourier phase. What we are saying here is that you really just need to have two condensates. Here, a nematic superconductor in this case has is a two-dimensional representation. So there are two different condensates, and they also allow for a charge Fourier phase. Now, we don't know a lot about this state, the quartet state. As you said, it's expectation value of a 4 fermion operator. So even a mean field theory is a strong coupling theory because it's an interaction term. So there's this very nice paper by Yuxuan showing that this in general is going to be actually gapless, but it has a small superfluid density. The main manifestation would be the vortex quantization be half a flux instead of the full flux. And there has been a report, and I think the jury's out, whether you could have, they saw signatures that are consistent with half and a third flux quantum in these Kagome superconductors, which could be consistent with charge 40 and charge 60 in this paper here. But this is just to show that there is a now, we can look for this charge 40 in nematic superconductors, a different framework to look for them. So I just wanted to mention that, this idea, I gave two examples where there are applications to real materials, to compounds. We also discussed this in other compounds. There's this titanium oxypnictide, heavy fermions, or this intercalated compound. I'm not going to go into details. These are all, or these two are collaborations with experimentalists to explain experimental data. And, there are lots of ideas floating and expanding this idea of vestigial phases to other frameworks, including, for example, in ultra-cold atoms. And again, this is not going to solve all the problems that we have, but it is interesting that it offers, from a phenomenological point of view, interesting new information that wouldn't be available and otherwise, and that you can actually get from phenomenology. And one exciting prospect is to connect this to topology, but this is probably the topic for a future talk. So I'm going to leave you here with my conclusions. So I hope I convince you that this idea of vestigial orders provide a very nice, simple, and powerful framework to describe intertwined orders in quantum materials. And there are lots of interesting applications in real materials. And it allows you to search for exotic collective electronic behavior, such as I told you, a spin current order or the charge Fourier state. And thanks for your attention.
Thank you for a great talk. Do we have any questions? Please just go forward and ask. Just go ahead.
Hello. Thank you for the talk. I have a question.
Hi.
So does this analysis extend to topological phases and topological order parameters?
So that is one of the things that I'm very interested in looking. I think yes, but we need to qualify which kind of topological order parameter. So for example, there are certain spin liquid phases that break crystalline symmetries, right? So, and those order parameters are not, they're not your standard Landau-like order parameters, right? They are topological in nature. So I think it'd be very interesting to look at how, how one could extend this formalism to that case. Now, the formalism we developed here is, there are two parts. One is the formalism that is based entirely on group theory. And essentially, all we need is a non-abelian group and look at one of the multidimensional Russo representations. And then there's another part, which is once you have this classification to do microscopic or phenomenological calculations of Ginzburg-Landau free energies to get these orders. Those are different, those are different things. So for what you're describing, if I remember correctly, there is this description of spin liquids in terms of, I think, projective groups, I think. So this could be, I don't remember exactly, but this could be one way of trying to extend that formalism there. So I think it's possible. I think the opportunity is there, but, I don't have anything smarter to say at this point.
Okay, thank you.
Any other questions? I have another question. So, what type of phenomena one could expect to be in the middle in this vestigial phases that, I don't know, they may not be happen in the low temperature phase?
Yeah, so I think one example, let me go back here, is that, for example, was the example that in the spin current order phase of the spin vortex crystal, you can actually get these Weyl points that they're not going to necessarily, appear in the magnetically ordered state. Another example that I could think of is for, think of the pneumatic phase, right? This pneumatic phase has enhanced magnetic fluctuations once you go to them. So you could see a situation where, because you have such a strong buildup of magnetic fluctuations inside that small window, you could get a precursor phenomena, like pseudo gap kind of precursor phenomena. So yeah, so the vestigial phase can have its own, properties that can be very different, or have different manifestations in the electronic degrees of freedom than the ordered state, because it only breaks a subset of the symmetries, but not all of them.
Okay, I see. Thank you. And another question about for charge superconductivity. So it's assumed that it's not energetically favorable to have usual Cooper pairs. So something doesn't allow to do it, but instead you are allowed to form 4-particle Cooper pairs. Is it picture?
The way I think is the other way around. Let's say there is the system wants to form two condensates, right? Two different kinds of pairs, if you wish. And in that case, we just go here. In this case was this zeta 1 and zeta 2, which I don't know where I introduced. Maybe it was back here. Yes. So zeta 1 and zeta 2. So if I one example would be in the hexagonal lattice would be a dx square minus y square wave and a dxy wave. So these are two condensates that, because of symmetry, they have to condense at the same temperature, right? So the key point is that once they condense, then they know about each other, so they acquire relative phase or whatnot, right? So the idea is that these two condensates, before each one of them form a condensate, they can themselves form a condensate of condensates, very similar to what I mentioned about this idea from Nozières about 40 years ago of where, can I have a condensation of pairs of bosons before the Bose-Einstein condensation per se? And the answer is actually yes. I mean, you need another species. You can't have one single boson species. You have to have flavors. And to some extent, the two condensates are doing that for you. But you do have, I mean, the ground state is Cooper pair, but you can, but you once you melt it, you can retain this idea of having both of them together.
If we have chiral superconductivity with Px plus I plus minus IPy, so you have two competing topological
right.
states.
So the idea there is that you could have a ferromagnetic phase and a chiral phase, so a phase that breaks time reversal but is not superconducting yet. And if I remember correctly, there has been a report of that this phase may be realized in one of these iron-based superconductors, and also in a new superconductor called 4Hb tantalum disulfide. We can talk more about these materials, but yeah, that could happen. Yeah.
Okay, so I see. Very interesting. Very interesting. Okay. Any other questions? Please just go ahead.
Yes, hi. I have maybe one question. Thank you for your talk.
Thank you.
Okay, I think maybe it's related with your last comment and with this line actually. So you mentioned chiral superconductors, but I think so. Then I think that you explain more work on this pneumatic superconductor. So I was wondering if there are some work or experimental or theoretical on this kind of vestigial order for chiral superconductors.
Yeah. I cited some of them here.
Okay.
Yeah. So yeah, no, there are works. I think this work here by Sudbo, if I remember correctly, I think that's one of the phases they discussed. Babayev and Sudbo, I think they mentioned this phase. They discussed this phase that breaks time reversal here. I don't remember if it's exactly this reference or another one, but there was this discussion before. There was another paper that I'm not citing here in this list because I don't have space, by Erisberg and Mark Fisher, in the context of strontium ruthenate, the 214. That, remember, people thought for a while this was a P plus IP, and they also had this discussion that it could break time reversal. And Roland Villa also has a theoretical work describing the situation, also in ruthenate, not from the P plus IP perspective, but from accidental degeneration. So yeah, there are several theoretical works. I'll be happy to send you those, on an email.
Okay,
And there is at least there are at least two experiments that are consistent with this idea. Okay, I'm not sure, I wouldn't call smoking gun, but they show evidence of a phase that breaks time reversal above the superconducting phase. Whether this is a vestigial phase or something else, I think we don't know yet.
Okay, interesting. Thank you.
Any other questions? You have last chance. If not, let's thank you the speaker again.
Thank you very much.
Thank you for your talk, Rafael.
Thank you.